In mathematics, a finite set is a set that has a finite number of elements. For example, is a finite set with 5 elements. The number of elements of a finite set is a natural number and is called the cardinality of the set. A set that is not finite is called infinite. For example, the set of all positive integers is infinite. Finite sets are particularly important in combinatorics, the mathematical study of counting. Many arguments involving finite sets rely on the Pigeonhole Principle, which states that there cannot exist an injective function from a larger finite set to a smaller finite set. Definition and terminology. Formally, a set S is called finite if there exists a bijection for some natural number n. The number n is the set's cardinality, denoted as S. The empty set, or O, is considered finite, with cardinality 0. If a set is finite, its elements may be written, in many ways, in a sequence. In combinatorics, a finite set with n elements is sometimes called an n-set and a subset with k elements is called a k-subset. For example, the set 5, 6, 7 is a 3-set, a finite set with 3 elements, and 6, 7 is a 2-subset of it. Basic properties. Any proper subset of a finite set S is finite and has fewer elements than S itself. As a consequence, there cannot exist a bijection between a finite set S and a proper subset of S. Any set with this property is called Dedekind finite. Using the standard ZFC axioms for set theory, every Dedekind finite set is also finite, but this requires at least the axiom of countable choice. Any injective function between two finite sets of the same cardinality is also a surjective function. Similarly, any surjection between two finite sets of the same cardinality is also an injection. The union of two finite sets is finite, with in fact. More generally, the union of any finite number of finite sets is finite. The Cartesian product of finite sets is also finite, with. Similarly, the Cartesian product of finitely many finite sets is finite. A finite set with n elements has 2n distinct subsets. That is, the power set of a finite set is finite, with cardinality 2n. Any subset of a finite set is finite. The set of values of a function when applied to elements of a finite set is finite. All finite sets are countable, but not all countable sets are finite. The free semilattice over a finite set is the set of its non-empty subsets, with the join operation being given by set union. Necessary and sufficient conditions for finiteness. In Zermelo-Fraenkel set theory without the axiom of choice, the following conditions are all equivalent. S is a finite set. That is, S can be placed into a one-to-one correspondence with the set of those natural numbers less than some specific natural number. S has all properties which can be proved by mathematical induction beginning with the empty set and adding one new element at a time. S can be given a total ordering which is well ordered both forwards and backwards. That is, every non-empty subset of S has both the least and the greatest element in the subset. Every one-to-one function from P into itself is onto. That is, the power set of S is Dedekind finite. Every surjective function from P onto itself is one-to-one. Every non-empty family of subsets of S has a minimal element with respect to inclusion. S can be well-ordered and any two well-orderings on it are order isomorphic. In other words, the well-orderings on S have exactly one order type. If the axiom of choice is also assumed, then the following conditions are all equivalent. S is a finite set. Every one-to-one function from S into itself is onto. Every surjective function from S onto itself is one-to-one. S is empty or every partial ordering of S contains a maximal element. Foundational issues. Georg Cantor initiated his theory of sets in order to provide a mathematical treatment of infinite sets. Thus the distinction between the finite and the infinite lies at the core of set theory. Certain foundationalists, the strict finitists, reject the existence of infinite sets and thus advocate a mathematics based solely on finite sets. Mainstream mathematicians consider strict finitism too confining, but acknowledge its relative consistency. The universe of hereditarily finite sets constitutes a model of Zermelo-Fraenkel set theory with the axiom of infinity replaced by its negation. Even for those mathematicians who embrace infinite sets, in certain important contexts, the formal distinction between the finite and the infinite can remain a delicate matter. The difficulty stems from Gödel's incompleteness theorems. One can interpret the theory of hereditarily finite sets within Peano arithmetic, so the incompleteness of the theory of Peano arithmetic implies that of the theory of hereditarily finite sets. In particular, there exists a plethora of so-called non-standard models of both theories, a seeming paradox. Non-standard models of the theory of hereditarily finite sets contain infinite sets, but these infinite sets look finite from within the model. On account of the incompleteness theorems, no first-order predicate, nor even any recursive scheme of first-order predicates, can characterize the standard part of all such models. So, at least from the point of view of first-order logic, one can only hope to characterize finiteness approximately. More generally, informal notions like set, and particularly finite set, may receive interpretations across a range of formal systems varying in their axiomatics and logical apparatus. The best-known axiomatic set theories include Zermelo-Fraenkel set theory, Zermelo-Fraenkel set theory with the axiom of choice, von Neumann-Bernays Gödel's set theory, non-well-founded set theory, Bertrand Russell's type theory, and all the theories of their various models. One may also choose among classical first-order logic, various higher-order logics, and intuitionistic logic. A formalist might see the meaning of set varying from system to system. A Platonist might view particular formal systems as approximating an underlying reality. Set theoretic definitions of finiteness. In contexts where the notion of natural number sits logically prior to any notion of set, one can define a set S as finite if S admits a bijection to some set of natural numbers of the form. Mathematicians more typically choose to ground notions of number in set theory. For example, they might model natural numbers by the order types of finite well-ordered sets. Such an approach requires a structural definition of finiteness that does not depend on natural numbers. Interestingly, various properties that single out the finite sets among all sets in the theory ZFC turn out logically inequivalent in weaker systems such as ZF or intuitionistic set theories. Two definitions feature prominently in the literature, one due to Richard Dedekind, the other to Kazimierz Kuratowski. A set S is called Dedekind infinite if there exists an injective, non-surjective function. Such a function exhibits a bijection between S and a proper subset of S, namely the image of F. Given a Dedekind infinite set S, a function F, and an element X that is not in the image of F, we can form an infinite sequence of distinct elements of S, namely. Conversely, given the sequence in S consisting of distinct elements, we can define a function f such that an element in the sequence in f behaves like the identity function otherwise. Thus Dedekind infinite sets contain subsets that correspond bijectively with the natural numbers. Dedekind finite naturally means that every injective self-map is also surjective. Kuratowski finiteness is defined as follows. Given any set S, the binary operation of union endows the power set P with the structure of a semilattice. Writing K for the subsemilattice generated by the empty set and the singletons, call set S Kuratowski finite if S itself belongs to K. Intuitively, K consists of the finite subsets of S. Crucially, one does not need induction, recursion or a definition of natural numbers to define generated by, since one may obtain K simply by taking the intersection of all subsemilattices containing the empty set and the singletons. Readers unfamiliar with semi-lattices and other notions of abstract algebra may prefer an entirely elementary formulation. Kuratowski finite means S lies in the set K, constructed as follows. Write M for the set of all subsets X of P such that X contains the empty set. For every set T in P, if X contains T, then X also contains the union of T with any singleton. Then K may be defined as the intersection of M. In ZF, Kuratowski finite implies Dedekind finite, but not vice versa. In the parlance of a popular pedagogical formulation, when the axiom of choice fails badly, one may have an infinite family of socks with no way to choose one sock from more than finitely many of the pairs. That would make the set of such socks Dedekind finite. There can be no infinite sequence of socks, because such a sequence would allow a choice of one sock for infinitely many pairs by choosing the first sock in the sequence. However, Kuratowski finiteness would fail for the same set of socks. Other concepts of finiteness in ZF set theory without the axiom of choice. The following concepts of finiteness for a set S are distinct. They are arranged in strictly decreasing order of strength. In other words, if a set S meets one of the criteria in this list, it meets all of the criteria which follow that one. In the absence of the axiom of choice, the reverse implications are all unprovable. If the axiom of choice is assumed, then all of these concepts are equivalent. I finite. Every non-empty set of subsets of S has a maximal element. I finite. For every partition of S into two sets, at least one of the two sets is I finite. E finite. Every non-empty monotone set of subsets of S has a maximal element. I finite. The power set P is Dedekind finite. IV finite. S is Dedekind finite. V finite. S equals 0 or 2S greater than S. Vi finite. S equals 0 or S equals 1 or S squared greater than S. 7 finite. S is I finite or not well orderable. The forward implications are theorems within ZF. Counterexamples to the reverse implications are found using model theory. Most of these finiteness definitions and their names are attributed to Tashi 1954 by Howard and Rubin 1998. 278. However, definitions I, II, III, IV and V were presented in Tashi 1924, pp. 49-93, together with proofs for the forward implications. At that time, model theory was not sufficiently advanced to find the counterexamples.